let us start with a numerical example based on schema theorem of a binary coded GA. Now, supposing that we have got the random initial population of size n equals to 10 of a binary coded GA as follows. So, here we are going to show 10 GA string and each GA string consists of 6 bits. So, this is the initial population. Now, the fitness of a GA string is assumed to be equal to its decoded value. Calculate the expected number of strings to be represented by the schema H, which is nothing but star 1 star star 1 star at the end of first generation, considering a single point crossover of probability P c equals to 0.9 and a bitwise mutation of probability P m equals to 0.01. Solution. Now, here actually what I am going to do, I am just going to calculate the fitness of all the GA strings, and as we mentioned that the fitness is nothing but the decoded value of this particular the GA string. Now, for the first GA string, that is 100,100, its decoded value will be 36. Now, this is the way actually we calculate the decoded value. So, 0 multiplied by 2 raised to the power 0 plus 0 multiplied by 2 raised to the power 1 plus 1 multiplied by 2 raised to the power 2 plus 0 multiplied by 2 raised to the power 3 plus 0 multiplied by 2 raised to the power 4 plus 1 multiplied by 2 raised to the power 5. So, if we calculate, you will be getting 36. Now, similarly, for all the GA string, we try to find out their decoded values for all 10 GA strings. And once you have got the fitness information for all the GA string, so I can find out the total fitness, and it is coming to be equal to 333. And once you have got this particular the fitness values for the whole population, now I can find out the average fitness, and that is nothing but f bar, that is 333 divided by 10, that is 33.3. So, this is the average fitness of this whole population. Now, the schema H, which is nothing but star 1 star star 1 star. So, this particular schema is followed by a few GA string, and those are as follows. For example, from this whole population, only the third one. So, this particular GA string, then comes your the fifth one, that is this particular GA string, and the ninth one, that is this particular GA string, are going to follow that schema H. And here, corresponding to this particular the GA string, we have got the decoded value or the fitness value as 23. For this particular GA string, the decoded value or the fitness value is 22, and this particular GA string, the fitness or the decoded value is 51. So, very easily we can find out what should be the average fitness for the schema. So, if H is nothing but the schema fitness or the average fitness of the schema, and that is nothing but 23 plus 22 plus 51 divided by 3, and that is equals to 32. And here M h comma 1, that is nothing but the number of string which is going to follow schema H at the present iteration, and that is nothing but the 3. Now, we can find out that P c equals to 0.9, P m equals to 0.01, and the length of the string denoted by capital L is nothing but 6, and delta H, that is the defining length of this particular the schema, that is nothing but the difference between the last and first. The last fixed bit is nothing but the fifth one, and the first fixed bit is nothing but the second one. So, the defining length is nothing but 5 minus 2, and that is equals to 3, and order of schema H, that is nothing but the number of fixed bit, and that is equal to 2. Now, I am just going to use this particular the equation or inequation, that is m h comma 2 is greater than equals to m h comma 1 f h divided by f bar multiplied by 1 minus P c delta H divided by L minus 1 minus order of H multiplied by P m. Now, if this particular expression, so the terms within this third bracket, that indicates actually the probability of survival, and this f h is nothing but the schema fitness, f bar is the average fitness for the whole population. And now, if I substitute the numerical values, so I will be getting the expression for this particular m h comma 2. Now, here m h 1 is equals to 3, f h is equals to 32, f bar is 33.3, 1 minus P c is 0.9, delta H is 3, L minus 1 is nothing but 5, minus order of H is 2 multiplied by P m 0.01, and if I calculate, so this will become equal to this, is greater than equals to 1.268. Now, let me consider say 2, or I can also consider 1. That means, in the present iteration, the number of string which is following schema H, it is 3, but in the next iteration it is found to be less than 3, either it is 1 or 2. That means, so the number of string which is going to follow schema H is going to be reduced with the increase in iteration number. Now, let us try to find out the reason behind this. Now, to find out the reason behind this, let us first concentrate on the f h and f bar. So, f h is the schema fitness and f bar is the average fitness. Now, here the schema fitness, that is f h, is less than f bar, and moreover, if you just see that this defining length, that is delta h. So, delta h is equal to 3. Now, here we have got the number of bits in a GA string, that is equals to 6. So, L minus 1 is 5. So, 3 out of this 5, that is 3 divided by 5 is a high value. So, this particular probability of destruction, that is the probability that the crossover site will fall within the defining length, is high, and that is why actually we are getting the less value for this particular the number of string which is going to follow schema H in the next iteration. Now, according to the schema theorem or the building block hypothesis, so this particular schema H is not a good schema, because here the schema fitness is found to be less than the average fitness of the population, and this particular defining length, it is not a short defining length, it is a actually a large defining length. And due to this particular reason, so this particular the schema is not found to be good, and it is going to decay with the number of iterations. So, this is not a good schema. So, with the help of this particular numerical example, I think now the schema theorem for the binary coded GA is very much clear. Now, I am just going to start with the limitations of binary coded GA. Now, as I mentioned several times, that the first version of GA, which was proposed in the year 1965 by Professor John Holland, that GA was a binary coded GA. Now, binary coded GA is little bit easy to understand and it has got some applications also. However, so this particular binary coded GA has got a few limitations. Now, let me try to concentrate on the demerits or the limitations of this binary coded GA. Now, this binary coded GA is unable to yield any arbitrary precision in the solution. The reason I have already discussed that if I want to get a good precision in the values of the variables, so I will have to assign a large number of bits. Now, if I assign a large number of bits and supposing that I have got a few variables, 10 variables, in that case the length of the GA string will be large, and if length of the GA string increases, the computational complexity will also increase and consequently the GA will become slow, which is not desirable. Now, to overcome this particular problem of binary coded GA, nowadays we use the real coded GA, where the variables, the real variables will be represented using the real numbers. For example, the value of a particular variable could be 10.85 or say 15.65 and so on. So, directly we are going to use the real values for the real variables inside the GA solution. So, this particular the principle of real coded GA I am going to discuss in much more details after some time. The next is this binary coded GA is going to follow and it is going to face, I should say, some sort of a problem that is called the Hamming-Cliff problem. Now, let us try to understand what do you mean by this Hamming-Cliff problem. Now, in binary codes, the way we represent, so this particular number say 14. So, 14 is represented as 0, 1, 1, 1, 0. Next 15 is represented by 0, 1, 1, 1, 1 and 16 is represented by 1, 0, 0, 0, 0. Now, this is the way actually we represent the number in binary. Now, if I see that how many bits are to be changed, if I want to move from one number to the next number. For example, say from 14 to 15 if I want to move, so there will be only one change, that means this particular 0 is made 1 here. Similarly, if I want to move from 15 to 16, I need 5 changes. For example, the 0 has to be converted to 1, 1 should be 0, 1 should be 0, 1 should be 0, 1 should be changed to 0. So, there are 5 changes if I want to move from 15 to 16. That means, in binary coding from a particular number, if I want to move to the next number or if I want to move to the previous number, the number of changes in the bits is not the same, and this particular problem is known as the Hamming-Cliff problem of a binary code. Now, this Hamming-Cliff problem is going to create an artificial hindrance to the gradual search of this particular the GA. Now, if I want to ensure a very good search, very efficient search for this particular GA, so what I will have to do is I will have to ensure a gradual search. The search cannot be abrupt, and to ensure this particular gradual search, in fact, we will have to take the help of another coding, and that particular coding is known as the gray coding. Now, this problem, the Hamming-Cliff problem of binary codes, can be overcome using the concept of the gray codes. Now, let us try to discuss little bit on the gray codes. Now, in gray codes actually what we do, 0 can be represented using 0, 0, 0, 0, 1 can be represented 0, 0, 0, 1, then comes your 2 can be represented 0, 0, 1, 1. Now, here if you see, so from 0 to 1 if I want to change, so I need only one change. So, to move from 0 to 1 I need only one change, that means this particular 0 has to be converted to 1. Similarly, if I want to move from 1 to 2, I need once again only one change, that means this particular 0 has to be converted to 1. So, I have got one change here, I have got one change here. So, in gray code, if I want to move from a particular number to the next number, or if I want to move to the previous number, there will be fixed number of change and that is equal to 1. And this actually gives some sort of advantage over the binary codes. So, nowadays, so this binary coded GA has been replaced by the gray coded GA.